Hey everyone, welcome to today's Explainer. I am absolutely thrilled to guide you through this material today, because we are looking at one of the most fundamentally fascinating branches of physics, optics. This is the study of exactly how light behaves and how it interacts with matter. What's truly mind-bending right off the bat is that light doesn't just play by one set of rules. As you probably know, it behaves as both a wave and a particle, a photon. But for our purposes today, in the realm of geometrical optics, we're going to treat light as rays traveling in perfectly straight lines.
Okay, let's dive into this. Have you ever looked at a glass of water with a pencil resting in it and thought, why does that look completely snapped in half? Or perhaps you've marveled at how a diamond somehow manages to capture light and just explode with sparkle. Well, these aren't just random, unexplainable illusions. They're the direct result of the strict, highly predictable rules of optics. By the end of this explainer, you're going to know exactly the mechanics behind these everyday mysteries.
But before we get into what light does when it hits stuff, we've got to talk about how it moves. 3 times 10 to the 8th power. That is 300 million meters per second. That's the staggering speed of light in a vacuum. To put that into perspective, light is basically the fastest made character in the entire universe. And a key property here is its rectilinear propagation, which is just a fancy way of saying it travels in perfectly straight lines, completely unbothered until it finally interacts with an object.
Act 1. Bouncing light. The rules of reflection.
So what is reflection? Simply put, it's the phenomenon where light bounces right back into the exact same medium after it strikes a surface. Think of it like throwing a tennis ball against a solid brick wall. The light ray comes in, hits the boundary, and is sent right back into the air or the space it came from. But here's the thing, it doesn't just bounce randomly. It follows a very strict code of conduct.
What's truly fascinating here is how simple and elegant these two laws of reflection are. Law 1 states that the angle of incidence is exactly equal to the angle of reflection. If light hits a mirror at a 45-degree angle, it leaves at a 45-degree angle. Boom. Law 2 states that the incoming ray, the outgoing reflected ray, and the normal, which is just our term for an imaginary line perfectly perpendicular to the surface, all lie flat in the exact same plane. It is literal geometric perfection.
Now, you might be wondering, if light always follows these exact laws, why can I see my face perfectly in a mirror, but not on a plain white wall? Well, it all comes down to the surface itself. Regular or specular reflection happens on incredibly smooth surfaces, which perfectly preserves the rays to produce a clear image. Diffuse reflection, though, happens on rough surfaces. Those microscopic bumps and ridges scatter the light in a million directions. The laws are absolutely still being followed by every single individual ray, but the collective image, completely scrambled.
And that brings us to mirrors, which engineer that smooth reflection for us. A standard plane mirror gives you an image that's virtual, upright, the exact same size, and laterally inverted, which, by the way, is exactly why the text on your shirt looks backwards in the bathroom mirror. But if we curve the mirror, we completely change reality. A concave converging mirror can actually form either real or virtual images depending on where you stand. A convex diverging mirror, on the other hand, will always give you a virtual shrunken-down image. Just think of the passenger side mirror on your car.
The best part is, we don't have to just guess what kind of image we're going to get. We have the mirror formula. This brilliant little equation relates the focal length of the mirror to the exact distances of the object and its resulting image. And this brilliantly illustrates the true power of physics, right? We can mathematically calculate precisely where an image will appear and exactly how magnified it'll be before we ever even build the mirror.
Act 2. Bending light. The reality of refraction.
All right, so if reflection is bouncing, refraction is bending. It's defined as the bending of light when it passes from one medium to another. But the absolutely crucial part to understand here is the why. It happens due to a change in speed. Remember that 300 million meters per second? Yeah, that's strictly in a vacuum. When light enters water or glass, it actually slows down. And just like a shopping cart hitting a patch of mud at an angle, that sudden change in speed causes a dramatic change in direction. And just like reflection, refraction has its own rulebook, primarily governed by Snell's law. The first law is super familiar. All the rays lie in the same plane. But the second law introduces the refractive index. This is a mathematical ratio representing exactly how much a specific medium slows light down. Snell's law tells us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is completely constant for those two given media.
Let's build a really clear mental model for how this direction changes. When light travels from a rarer medium, like air, into a denser medium, like glass, it slows down and it bends towards that perpendicular normal line.
Conversely, when it travels from a denser medium back out into a rarer one, it speeds back up, bending away from the normal. Once you picture it, it's an incredibly predictable dance. We actually harness this bending power every single day using lenses. A convex lens is thicker in the middle and converges light rays to a single point, creating real or virtual images depending on the distance. A concave lens is thinner in the middle, diverging the light, and it always creates a virtual image. And just like with our mirrors, we have a precise lens formula linking the focal length with object and image distances. This exact math is literally how your camera focuses and how your eyeglasses instantly correct your vision.
Act 3. The magic trick. Total internal reflection and dispersion. Okay, first up in our magic tricks is total internal reflection, or TIR. Imagine light trying to escape from a dense medium like water out into a rarer medium like air. If it hits that boundary at an angle perfectly exceeding what we call the critical angle, it doesn't actually refract out. Instead, it gets completely reflected back inside. The surface essentially acts like a perfect mirror. The light is trapped.
Then we have dispersion, which is the truly beautiful splitting of white light into its constituent colors. And it's actually just a side effect of refraction. You see, different wavelengths, meaning different colors, refract or bend at slightly different angles. Red bends the least, violet bends the most. And this, quite literally, is the exact recipe for a rainbow.
Now look, these aren't just abstract textbook concepts. They actively build our modern world. Total internal reflection? That's the secret behind optical fibers. It traps pulses of light to power our high-speed global internet. And it allows doctors to see inside the human body with endoscopy. It's the whole reason diamonds sparkle so brilliantly. Meanwhile, everyday reflection and refraction are hard at work inside our telescopes, microscopes, and periscopes.
Act 4, Reality Check, comparing the concepts and avoiding mistakes.
So let's put these two heavyweights head-to-head for a second so we can lock them in. Reflection is all about light bouncing back. Refraction is about light bending. In reflection, the light stays in the exact same medium. In refraction, it crosses into a totally new one. And crucially, in reflection, the speed of light stays constant. But in refraction, the change in speed is the entire reason the bending happens in the first place. Now, as you apply all this, please watch out for these incredibly common pitfalls. So the absolute crucial point is this first one. Never ever measure your angles from the surface of the mirror or the glass. Seriously, always measure from the normal, that imaginary perpendicular line. Also, be super careful not to mix up your bouncing with your bending, and when you're using those mirror and lens formulas, pay strict attention to your positive and negative sign conventions.
We started off this explainer by asking why pencils bend in water and why diamonds sparkle. Well, now you know for sure, it's refraction and total internal reflection. But I want to leave you with one final question to ponder based on our source material today. We know light bends, and we know it bounces, but why is the sky blue? I'll give you a hint. It has to do with a fascinating concept called scattering, but that is a mystery for you to explore next. Thanks for joining me on this explainer, and keep questioning the world around you.